Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on July 30th, 2025, just yesterday. This paper introduces a new method that achieves an average 5.6% utility gain on downstream tasks and gets there 71% faster on average, all while maintaining the same strict privacy guarantees. The paper is titled, Efficient Differentially Private Fine-Tuning of LLMs via Reinforcement Learning, and the implications for training on sensitive data are pretty significant. It reframes the challenge of private fine-tuning as a control problem solved by reinforcement learning. Also, the authors shared their implementation on GitHub. If you check it out, you'll find the full code for RLDP, including the training scripts. It's all there, with clear instructions on how to run your own experiments using LoRa, the RL hyperpolicy, and even track your results with weights and biases. On Hugging Face, you can find the 7 billion parameter model, a fine-tune of Mistral. The weights are available for download, along with usage examples to get you started. So to really understand the challenge this paper tackles, let's look at the kind of data they're working with. This table shows a sample pseudo-clinical narrative, essentially a fake patient record. It includes details like race, age, and a unique secret id. This is precisely the type of sensitive information that needs protecting. That secret id is an example of a canary, a unique piece of data intentionally planted in the training set. Researchers then test if an attack, called a canary extraction attack, can force the model to reveal it, which would signal a major privacy breach. So, while protecting against attacks like canary extraction is crucial, the big question is always how much this privacy protection hurts the model's actual performance, its utility. The next set of figures, from 1 to 4, dive into exactly that. They measure this utility using a metric called perplexity. You can think of perplexity as how confused a model is by new text. A lower score is better, meaning the model is more confident in its predictions. They test this across models like GPT-2, Llama, and Mistral under different privacy budgets, controlled by a parameter called epsilon. A smaller epsilon means stricter privacy. Alright, this table lays out the results in black and white. It compares the final perplexity scores for different models, from GPT-2 all the way to Mistral 7b, across various privacy budgets. The standard way to do this kind of private training is with a method called Differentially Private Stochastic Gradient Descent, which adds carefully calibrated noise during training to protect data. This new method, RLDP, uses reinforcement learning to manage that process more intelligently. The bold numbers are for RLDP, and the numbers after the arrow are for the best competing method. In every single cell, RLDP wins. So not only does RLDP achieve better final performance, this table shows it gets there much faster. It details the fraction of training steps, or optimizer steps, that RLDP needs to match the final utility of the best baseline method. A value of 25% means RLDP converged 4 times faster. And look at the Mistral 7b model under the tightest privacy budget. It only needed 13% of the training time. On average, RLDP reaches the same performance using only about a quarter of the training budget, a massive efficiency gain. So, in conclusion, by using reinforcement learning to intelligently manage the privacy budget, RLDP not only achieves better model performance, but does so with a massive speed up. It's a powerful new approach to the long-standing privacy versus utility problem. That's it for this episode of the